All right, good afternoon, everyone. Welcome to October's First Friday webinar. This is HSHS Pedestrian Bridge Project with Ryne Fiorito. My name's Ariana. I'm the Education Specialist with ISPE. So as always, if you have any questions regarding today's webinar or our other education programs, please feel free to reach out. I just have a few quick announcements and then we'll get started. Firstly, the handouts for this presentation are available in the handouts section of your taskbar. They're also available on our website along with the quiz link. Just ask to please complete the quiz by next Wednesday so we can get your PDA certificates out to you as soon as possible. If you have a question for Ryne at any time during the presentation, please type it in the questions box of your taskbar along with the slide number that corresponds with your question. You can find the slide numbers at the bottom right-hand corner of Ryne's presentation. I will go ahead and read those questions out loud at the end. I think that's all. So with that, I'll go ahead and hand it over to Ryne.
Thanks, Ariana. And thank you to ISP for inviting me to present for the this First Friday in the SE Bootcamp. It's an honor as a new SE to be presenting to everybody today. As an introduction to the Sky Bridge project, HSHS St. John's in Springfield, Illinois, was to construct a new pedestrian bridge as part of a larger project on the east side of their campus. St. John's contracted with a developer to build the new medical office building, or MOB, on the east side of 9th Street, across from the existing Carol Trevecchi building. The Carol Trevecchi building is the existing children's hospital for St. John's, and the new MOB will be the Outpatient Center for Women and Children. St. John's needed a connection between these two buildings for patients and staff to get from one building to the other safely, and a crosswalk at this location at 9th Street was not an option for the site. A pedestrian bridge, or Skylink, is what HSHS is calling it, links the two buildings over 9th Street. The new bridge would have two spans, one of 86 feet over 9th Street and the other 65 feet over the new MOB entrance. Since 9th Street is an Illinois state route, the construction plans had to be reviewed by the Illinois Department of Transportation, Bureau of Bridges and Structures for approval. During the review process, IDOT required certain clearances to the right-of-way, as well as overhead and airspace clearances for the route. The topics we'll cover in the presentation today include the parties involved, the design codes we used, the bridge design itself, the bridge fabrication, and then finally the bridge installation. The owner for the project is Hospital Sisters Health System, St. John's Hospital in Springfield, Illinois. The general contractor for this part of the project was O'Shea Builders from Springfield, Illinois. And O'Shea contracted with Intertech PSI from Springfield to perform the drill pier inspection and concrete testing. The architectural work on the project, along with the mechanical, electrical, and plumbing engineering, was performed by Berner Schober Architect from Green Bay, Wisconsin, and the civil, structural, and geotechnical engineers were from Hanson. The structural design of the pedestrian bridge, for the structural design, we use several different codes for loadings. The AASHTO LRFD guide specifications for design of pedestrian bridges provided the design criteria for the wind loading. The wind loads covered by this guide describe the different conditions such as passing traffic and the natural wind events. And then based on this guide, we applied a variable linear uplift wind load to the underside of the bridge, which caused a worst case uplift design condition for the bridge. We also used this guide for the horizontal wind pressure. The 2015 International Building Code was used for the minimum gravity loads, as well as the minimum or the maximum slope for the bridge. And ASCE 710 was used for the design loads from Seismic. Since the structure is located in Springfield, the Springfield Code of Ordinances was used for the ground snow loading. For gravity loads, we used a 100 pounds per square foot live load for the bridge floor. This is a relatively high live load for most structures, but based on Hansen's past experience with pedestrian bridges in hospitals, it was selected to allow for future flexibility if needed. The roof live load of 20 pounds per square foot was selected for the construction loading, but did not control over the snow loading, which we'll talk about here in a second. The Springfield Code of Ordinances requires the ground snow load to be modified from ASCE 7, ground snow load of 20 pounds per square foot, up to 30 pounds per square foot. It also requires the minimum roof snow load to be 30 pounds per square foot. Other factors for snow, such as rain on snow, sliding snow, and drift loads, are still based on ASCE 7. The dead load of the steel truss structure was approximately 23 pounds per square foot, and the additional we added an additional 20 pounds per square foot for the collateral dead load from mechanical, electrical, and plumbing equipment supported by the bridge. The dead load used for the curtain wall system was 15 pounds per square foot over its exposed vertical face, and the concrete floor deck was a 5.5-inch lightweight concrete on composite metal decking. And that floor system had a dead load of 45 pounds per square foot. For the wind loading, the design velocity from the AASHTO guide was 115 miles per hour. From the exposure category, and using exposure category C was conservatively selected for this site. Since emergency facilities for the hospital did not require the use of the bridge, risk category 2 was selected for the structure. Based on this criteria for the wind loading, the total wind pressure on the profile was 60 pounds per square foot, and includes the windward, and this includes the windward and leeward pressures. A reduced wind speed of 76 miles per hour was used for serviceability checks and resulted in a lateral pressure of 26 pounds per square foot. The uplift pressure from the AASHTO guide was combined with the lateral wind loads. The lateral wind load, as described earlier, was the variable linear load, and it had a maximum pressure of 53 pounds per square foot at the windward face and reduces to 0 10.5 feet in. The uplift wind loading combined with the horizontal wind loading produces an overturning moment that had to be resisted by portal frames and bearing connections located at each pier, which we'll discuss here soon. For seismic loading of the bridge, ASCE 7 was used. Based on Hansen's geotechnical investigation, site class C was determined to be appropriate for this site. Using site class C and the site accelerations from USGS, the seismic design category we were able to use was design category B. Using design category B for the structure allowed us to use a seismic force resisting system of steel systems not specifically detailed for seismic resistance. You may want to make note of that for the quiz at the end. The concrete piers were detailed for using ordinary reinforced concrete moment frames. The total seismic mass of the bridge was 465 kips, and the seismic base shear was 18 kips. Seismic loading controlled the longitudinal design of the bridge, and the drift in this direction for the structure was 1/4 of an inch. In the perpendicular direction, the wind loading controlled the design, and the drift in that direction was 3/8 of an inch. The pedestrian bridge was designed to be an independent structure between the Children's Hospital and the new MOB. Neither building was designed by Hansen, so determining the appropriate size of the expansion joint was not straightforward. The structural engineer for the MOB was Corda out of Columbus, Ohio, who provided Hansen with the design drift for the MOB. The MOB structure was laterally braced by steel brace frames, so the drift for this structure was relatively low. We also coordinated with Corda and Kaler Slater, the architect for the MOB, to detail the expansion joint between the MOB and the bridge. At the time of the design of the bridge, the MOB was under construction, and Kaler Slater had noted for the MOB contractor that this joint would need to be installed in the slab of the building at the bridge expansion joint. For the Children's Hospital, we used a maximum allowed drift load according to ASCE 7. The hospital is constructed of concrete frames, so the drift for this structure is also relatively low. After our analysis of the drifts and of each building and the bridge, the expansion joint size of 3 inches was selected for both the Children's Hospital and the MOB. We analyzed the structure of the bridge using RISA 3D. The wind, seismic, gravity loads were applied to the model, and code checks were performed on the steel components of the structure. The loading for the concrete piers was taken from the model, and then we designed those separately from the RISA model. The bridge ties the 3rd floor of the Children's Hospital on the west to the 3rd floor of the MOB on the east. This image here, the bridge elevation, is looking to the north, so west is on the left and east is on the right. The floors of the 2 buildings were not aligned due to the desired floor-to-floor height and site elevation of the new MOB. So this required the bridge floor to slope up to match the tie-in elevation at the new MOB. The slope of the bridge is approximately 2%, or about a 1/4 inch per foot over its length, and the total height differential over the length of the bridge is just over 3 feet. The roof of the bridge is pitched to match the floor toward the Children's Hospital, and stormwater on the roof is collected at the pier next to the Children's Hospital. Each bridge truss is a Warren type truss, 11 feet 10 inches tall and spaced 11 feet apart. The minimum clear distance from the bottom of the structure to the crown and 9th Street is 23.5 feet. And we had coordinated that distance with IDOT, and that was the clearance. That was a little more than they needed, but that was what we stuck with. The trusses for each span were connected together at the center pier for continuity of the top and bottom cords. This continuous 2-span condition for the pedestrian bridge over the center pier worked to reduce the vertical deflections in both spans. One concern with the center pier being next to a state route was the need for a crash wall to protect the support. Hansen analyzed the requirements for a crash wall, and it was determined that one was not required. All of the piers are on HSHS property, and they were set back far enough from the right-of-way that a barrier wasn't warranted. Nevertheless, as a precaution, we ran our model of the bridge without the center support in place and checked it without live load or wind loading, and having those trusses continuous over that center support allowed the bridge to support itself without the center pier and still doesn't have any members overstressed. This would be an extreme condition for the bridge, but it was a benefit to having the continuous connection at that center pier. At each end of the bridge, a cantilevered moment frame was used to fill the gap between the first pier and the building on each side. The moment frames also aided in making up the difference in the tie-in points for the buildings. So here we have this is our portal frame next to the Children's Hospital. We call it WCC in our plans here. But the moment frame that I'm talking about here is this C-shaped frame that is bolted to the portal frame, and then these are moment connections, top and bottom cords. Based on our survey, Hansen survey, and the layout of the MOB on the east site, we found that the face of the Children's Hospital was not parallel with 9th Street. The MOB was laid out to be parallel with 9th Street, though. Further complicating things for our survey, the coordinate system for the construction of the Children's Hospital was unknown. For the new construction, though, the horizontal control was based on NAD 83, and the vertical control was based on NAVD 88. Hansen's survey for the face of the building and floor elevations was critical to establish the bridge floor elevations and set its position. The horizontal alignment of the bridge had to miss certain obstructions within the Children's Hospital, but also fit within a column bay in the new MLB. This alignment constraint caused the bridge axis to not be parallel with 9th Street or either face of the either building. So the bridge was slightly skewed. The moment frames at each end of the truss were different lengths to make up the varying gap between the existing buildings. The floor of the moment frame portions of the bridge was level to match the floor elevations, and then this allowed for doorways at each pier to be installed without having to worry about the slope of the floor. To transmit the horizontal loads or lateral loads on the bridge to the foundations, we designed a horizontal truss in the plane of the roof and the floor to take those horizontal loads back to the portal frames. These horizontal trusses, along with the vertical trusses, created a space truss to help resist those lateral and vertical loads. The horizontal trusses also act to brace the main truss cords for compression, but also created a stiffer system for erection of each span. The system also allowed the bridge to be erected without the floor or roof diaphragm or any metal decking if the contractor chose to erect them without the metal decking. The lateral loads on the bridge due to the wind and seismic are resisted by steel portal frames at each pier. The loads on the bridge transmit the forces through the top and bottom horizontal trusses into the portal frames. The steel portal frames transmit those lateral loads into concrete piers, which are also portal frames, and then finally into caissons below. So here is a diagram of the loads and how they are resisted. So here we have the lateral loading applied to the floor or roof planes. The horizontal trusses then take those loads either way to the portal frame, so there's a portal frame at each pier. The portal frames resist those loads and get that load into the concrete portal frames at each pier, and then those portal frames get the load to the pier cap and finally into the caissons below. The steel portal frames at each pier were spaced 15 foot 6 inches apart, and this was done to define the supporting piers from the bridge. And it also gives the architectural appearance that the bridge itself is passing through the support. Framing over the top of the bridge continues the architectural definition of the piers, which are clad in metal panels. The light dashed lines in this detail here show the face of metal panels. And as you can see in this, at the roof, the overtop frame, there's a gap between the roof and this metal panel to allow for water to flow down the roof and not be interrupted at each pier. In addition to the moment, due to the lateral resistance of the bridge, the top and bottom portal frames required to resist out-of-plane bending for an unbalanced axial load from the truss cords. And as we discussed earlier, the truss cords are 11-foot centers, and they don't align with the portal frame columns. So in this image here, or this detail here, you can see the portal frame columns, and then these are the truss cords inset from them. So there's some unbalanced axial load that has to be resisted by the portal frame beam on the top or bottom. A roof davit tie-off system was also included for the roof of the bridge to allow for maintenance workers to be tied off when working from the roof. This was intended for a window washing or a future re-roofing project. The bearings of the bridge also required future maintenance to replace the elastomeric portions of the bearing system. In order to access the bearings, jacking points in the bottom portal frame member have web stiffeners, you see here, to resist the bridge dead load and some live load while the bridge is jacked up for bearing maintenance. Also in this image, you can see the concrete cross beam of the pier portal frame, and we are on the east and west piers. We have room for HVAC units that service the bridge that are bearing on that concrete cross beam. The bridge was designed with 2 fixed bearings and 1 expansion bearing. We used the IDA bridge manual as a guide for the design of these bearings. The center pier and the east pier were designed with fixed bearings, and the span between these 2 piers was 65 feet. We applied a thermal load due to a temperature differential of 70 degrees for design of the bearings and the anchorage and for design of the steel system. The thermal loading for this structure is lower than what a highway bridge structural engineer might use for a steel structure that could be 120 degrees in this area. Since the bridge is conditioned when it's completed, we felt the 70-degree differential was appropriate for the design. The west pier next to the Children's Hospital was designed as an expansion bearing. This was intended to limit the longitudinal loading from the bridge onto the drilled caissons, which are adjacent to a retaining wall for the lower level of the Children's Hospital. So if this is the expansion bearing, then longitudinal loads wouldn't get induced into the drilled caisson because there's a foundation wall for the Children's Hospital down low here. Here's our detail for the fixed bearing. You can see the rocker and the pintle for this condition, and then our expansion bearing detail. The foundation for the bridge consisted of drilled caissons bearing on rock to resist the gravity, lateral, and thermal loads from the bridge. 2 3-foot diameter caissons were installed for each of the 3 piers. The rock at the site was about 25 feet below grade, and the caissons were keyed into the rock 5 feet to develop their moment resistance for the caissons. The piers at the Children's Hospital side were about 6.5 feet from the face of the building, and the piers at the MOB side were 8.5 feet from the upper face of the building. A 5 foot deep by 5 foot wide pier cap ties the 2 caissons together, and there's a brick ledge that's cast atop the pier cap at each column to support the metal panels for the pier facade. 2 3-foot square columns are then cast atop the pier cap, and then a cross beam was cast monolithically with those columns to tie them together and act as a portal frame for the pier. The concrete for this the substructure elements of the bridge included a crystalline waterproofing admixture. We specified this admixture to help with corrosion protection of the reinforcement. So here we have the excavation for the pier next to the Children's Hospital. You can see inside these reinforcing the dowels from the drilled caissons, and then the dowels for the columns, and then sort of some of the reinforcement for the brick ledge. This is the pier next to the MOB. It's the same detail. You can see the dowels from the drilled caissons with the column dowels, and then the brick ledge reinforcing. Here's the completed pier cap for the MOB side. with the column dowels extending up. And then this is the completed pier next to the Children's Hospital with the crossbeam monolithically cast with the columns. The final elevations of the tops of piers were constructed within 1/8 inch of the plan elevations. Getting these piers that close to the plan elevations aided in getting the alignment of the floors to the Children's Hospital and MOB for the bridge. The framing for the bridge was fabricated by Savaggio Steel, located in Springfield, Illinois. The top and bottom chords of the 86-foot long truss were fabricated as one member without a splice. These beams were shipped to the fabrication shop approximately 90 feet long. According to Savaggio, this was the longest beam they had fabricated in their shop. The long length came at a slight premium for delivery from the mill, but a splice in the 86-foot long cord was not desirable. We also learned as part of this project that longer beams could also be ordered if they are needed, up to 140 feet long. Savaggio assembled each of the main trusses in their shop to ship to the site. Here they are flipping one of the 86-foot trusses so they can weld the web members on the opposite side. The steel portal frames for the bridge were also shop fabricated. The fabrication required complete joint penetration welds for the beam to column connections, and the column flange stiffener plates were also detailed with complete joint penetration welds. The bearing assemblies were milled by Johnson Machine Works and attached to portal frames at the fabrication shop. And here you can see the portal frame attached to the truss in the field before the erection. As you can see in this photo, the bearings received 3 coats of epoxy as required by IDOT. And you can also, in this photo, you can also see the web stiffeners for the jacking points on the portal frame. All the connections for the bridge, all the welded connections for the bridge except for one were specified to be shop welded, and then all the other connections in the field were bolted. O'Shea took delivery of the shop fabricated trusses at the site. For the span over 9th Street, O'Shea assembled the bridge on the ground so it could be lifted as one hoist. The assembly included all the floor beams, horizontal bracing, and moment frames, and roof and metal form deck and roof deck and mesh reinforcement for the bridge floor. By assembling the span over 9th Street for one hoist, this only required one short road closure to set the bridge framing over 9th Street. The span over the MOB drive lanes was they installed the shop fabricated trusses into place, and then floor beams and roof beams were installed in the air. For orientation, here's the elevation of the bridge again. So here you can see the span over 9th Street. So this was the truss they set, or the bridge portion they set is completed. And then this is the MOB side where this was installed in the air. Here's the field assembled span over 9th Street. So in the foreground here is the portal frame for the center pier. And then in the background, you can see the portal frame that will go against the Children's Hospital. And then this is the photo looking down the bridge with the metal deck and reinforcement already installed, and the metal deck for the roof as well. As many of you likely recall, this spring, the new pedestrian bridge for Florida International University suffered a collapse during construction. The collapse occurred on March 15, 2018, and the new pedestrian bridge at HSHS was scheduled to be erected on April 11, 2018. This event raised numerous concerns from numerous parties, including the hospital, and was on everyone's mind. This extreme event was a reminder of our duties as structural engineers to public safety and the risks that our work can have. Hansen discussed the bridge with the hospital and noted that the bridge was significantly different from the structure at FIU. FIU's bridge was intended to be a post-tension precast concrete structure with a cable stay pier, which was not yet in place prior to the collapse. As we've discussed, the 9th Street Bridge was a steel truss system. The collapse of the FIU bridge raised concerns about the erection of the 9th Street Bridge and how it would support itself prior to bringing its final condition. The FIU bridge was not complete at the time of the collapse, and the 9th Street Bridge was also partially installed and then was reopened to traffic. Our calculations for the hoisting and temporary condition of this bridge were rechecked and then checked again to confirm there would be no issues with the design during the erection and before the final condition. After everything was scrutinized thoroughly, there are no changes made to our design. For the bridge erection, we developed a suggested erection plan in the construction documents. The erection plan included the lift points, estimated weights, centers of gravity, and a suggested sequence for each lift. The documents placed the responsibility back on the contractor for a final lifting plan. The erection of the bridge over 9th Street was modified slightly by the contractor to include the end mullet frame adjacent to the Children's Hospital. Adding this frame to the 9th Street span produced a partial road closure to install that portion of the bridge between the pier and the existing hospital. With all the steel framing, metal decking, and reinforcement, the total lift for the span over 9th Street was approximately 62,000 pounds. 9th Street was closed on the evening of the lift between Madison Street and Carpenter Street to allow the contractor to set up the crane and lifts to place the hoist. Here's a excerpt from our erection plan. So it's still looking north. This is the span over 9th Street. We had thought about this would be the lift 1, followed by lift 2. So lift 1 included the portal frames on each side. Lift 2 would tie the MOB side to this existing portal frame, and then this portal frame would be set with that truss. And then 3 and 4 would be the end mullet frames. So they could be determined in the field just how long they need to be with that slight skew of the bridge. And they could field determine that length and then get it fabricated to fit. In order to set the bridge over 9th Street, 9th Street had to be completely closed. The closure of 9th Street had to occur when traffic volumes were low. The annual average daily traffic count for this portion of 9th Street is 10,150. Hansen collaborated with the City of Springfield and Illinois Department of Transportation, who helped us develop a traffic control plan that met the needs of this area and also did not block the emergency vehicle access to the hospital. Notices were sent out to ambulance companies to notify them of the closure and rerouting well in advance. So here's part of our traffic plan for the site. On the north end of the site, two-way traffic on Carpenter Street can get you bypassed around this portion that was closed, and then one-way traffic on Madison and Jefferson here was rerouted. The erection of the bridge over 9th Street went very smoothly. The road was closed about 8 p.m. to set up the crane. The wind speed on the evening of the lift was about 20 miles per hour, which was near the limit of what the crane operator was comfortable with to set the bridge. But the lift began anyway at about 9:30 p.m. The bridge was lifted from the assembly area on the east side of 9th Street and rotated in and over the piers and finally set atop the anchor bolts for the bearings. Once the bearings were bolted and welded into place, the equipment was cleared and the road was reopened at about 2:30 a.m. The total lift took about 4 hours from the time of lifting to finishing the bearings. So here we have a time-lapse video showing the erection of that span. So it's on the east side of 9th Street there, and they rotated in and toward the concrete piers. Then hoisted up. And finally boom over to the bearing seats. The portion of the span of the bridge over the new MOB entrance began 2 days after the 9th Street span was set. The contractor elected to assemble this span in the air to save time on the large crane, but it also because laydown area in front of the MOB was limited. The area to assemble both spans in that small location wasn't available to get both assemblies assembled in that one spot to efficiently use that large crane. The portal frame next to the MOB, you can see here, was set first, followed by the 2 trusses, shop fabricated trusses, and then they were bolted in the air to the portal frame. To account for the top cord being continuous over the pier, the erection plan included a note that the trusses would need to be slightly pitched to make that connection over the center portal frame. This was due to the slight dead load deflection of the 9th Street span. Once the alignment is made at the connection of the center pier and the connection was finished at the center pier, the MOB side truss is allowed to lower down and make it a connection to the portal frame on the MOB. Lowering that down induced tension in that top cord over the center pier for both spans. Since the trusses were erected without the roof beams or horizontal truss, the top cord did not have the lateral stability required for compression. The effective slenderness ratio, or the KL/R, for the top cord was equal to about 300, and for the MOB span, which was above the 200 for compression, according to the American Institute of Steel Construction. To get the slenderness limit, to achieve the slenderness limit, we required the contractor to brace that top cord at the center of that truss span. The bracing was only required for the out-of-plane buckling of the cord. The bracing load we calculated was relatively small and was accomplished by strapping the forks of telehandlers to the top cords until the roof beams and cross bracing was installed. You can see the telehandlers in place there now. They're not supporting the cord vertically, but just laterally, and then strapping those cords to the forks allowed the brace load to be taken in either horizontal direction. As you can see in this photo here, the last diagonal of the bridge to the portal frame connection is missing here, and that was due to the needing to set each piece individually. So the portal frame was set, then these trusses, and then that diagonal would go in the air. And then that was the only member here that was field welded. Here you can see the contractor installing the floor beams and then horizontal web members for the truss. Another photo, you can see the telehandlers holding or bracing that top cord, and then the completed installation, and they have the diagonal, that last diagonal one now, and then the head moment frame has been installed at that point too to tie in the floor to the MOB side. After the form deck, or the form deck and the roof deck was installed, 9th Street was fully closed once again on the evening of April 18th to cast the bridge floor. The concrete for the floor is lightweight concrete and reduced the dead load and seismic mass for the bridge. OSHA relied on their past experience in pumping lightweight concrete to elevated floor slabs and made sure their aggregates were pre-wetted by the ready-mix supplier to achieve the correct water-cement ratio and still allow the mix to be pumped. 2 pumps were utilized to cast the deck and ensured that the entire slab was cast that evening. The 2 pumps started at the center pier and worked their way out simultaneously away from the pier, which balances the load on the structure. The sides of the bridge were clad in glass curtain wall panels. Make note of that. The curtain wall panels are supported vertically and laterally from the bottom chord of the truss and laterally only from the top chord. This support condition allows for the truss to deflect while not stressing the curtain wall panel itself. The glass also allows for natural light in the bridge, but was selected to match the design of the new MOB. And just in case you're wondering, that blue strip is a plastic protection for the carpeting and not actually a feature of the bridge, although it's nicely lined up there. The underside of the bridge, as well as the bridge piers, were clad in metal panels that were attached to stud framing on the concrete or the steel structure. So here you can see the cross beam and then the HVAC unit that's serving the bridge, and this is the MOB side. This photo was taken when it's not quite complete, so they still have some metal panels on the top portion of the pier, and then some finish work to do on the rest of it, top and bottom soffits here. The installation of the curtain wall panels required, and metal panels on the piers required some partial lane closures of 9th Street due to the overhead work. Here you can see they're working on the curtain wall panel, and they've had this northbound, or the east northbound lane closed so they get their lifts in and get that portion of cladding installed. At this time, the bridge is nearly complete. Here's a view we took, or a shot we took Tuesday, and you can see this is looking to the south, the MOB here on the left. They had their glass curtain wall on this entrance side, and then it matches the glass on the bridge, and then there's a new facade on the Children's Hospital for a portion of that building. They're working on the metal panels here on the center pier and trying to finish up some of the stuff on the roof. This is a shot looking north. So you had the Children's Hospital and the new facade in that corner. And then here's a shot also looking to the north again. And you can see kind of this photo, it's hard and not made very clear, but the truck going underneath the bridge, there was plenty of clearance for larger vehicles to pass on the state route here. And with that, I'll open up to questions.
Okay, let's see here. It looks like we may only have one right now. Okay, we've got a few. So while we're answering these, if anyone has any further questions, go ahead and type them in now. Okay, so you may have answered this one, though I'm going to ask just in case. Who typically provides the structural steel connection detail on a project such as this?
For this project, we detailed all the steel connections. Sometimes there's typical floor connections that may be up to the fabricator, but for this project, we detailed all the connections.
What was the systemic force resisting system of the pedestrian bridge superstructure?
That was a steel system, not specifically detailed for seismic resistance.
Okay, and what is the project cost?
I don't have that number with me. I don't really have a good guess. The project, the entire project was several different items. So we had a parking garage that was part of the project. There's some other work around the site that was included in there too. So I don't have a cost for what the bridge was, or even the total project cost either.
Okay, so it looks like we did have one more question, though I think one of the attendees did answer it. The floor of the bridge was sloped at about 2%. Someone had asked what the slope of the floor of the bridge was. And then we have another question. I am not familiar with 9th Street. Is it an Illinois state route?
Yeah, 9th Street is an Illinois state route. It's Business 55 that, so as you come into Springfield from the south, 6th Street is Business 55, and then it transfers over to 9th Street at Lateral, and then it heads north from there.
Okay, does anyone else have any further questions for Ryne at this time? We'll give it about a minute. Okay, one other question has come through. Is there a wind tunnel effect between the buildings?
We didn't consider wind tunnel effect, but the reason we chose exposure category C, that's why we chose exposure category C, to kind of account for that. Perhaps the site could have been used. We probably could have used exposure category B, but to think about wind tunneling in that area, we'd have to have a study done, and that just wasn't part of the project. The loads on the stresses on the bridge due to the wind loads were well within the steel system and concrete could take, though.
Okay, another one. Do you typically review and stamp the fab shop's structural steel shop drawings prior to final build?
Since we did not, since we detailed all of the connections, those were sealed in our drawings. We didn't seal the fabrication shops at all, though. They just took our details and detailed the connections for dimensions and where they're going to put their copes, everything at, though.
Okay, I think that's about all the questions. Oh, one just came through, never mind. Okay, how different was this bridge to the FIUs? You mentioned you would comment on the difference again.
The SIU bridge, is multi-story. This bridge is one story. I think they're talking about the bridge over 6th Street. I don't know, that's not really similar.
You may have misunderstood me. FIU.
Oh, FIU. Okay. Yeah, the FIU bridge was a precast concrete with post-tensioning. So that was a different material. It had a cable stay, which it also had a concrete truss system as well, but it had a cable stay that wasn't in place yet. So the construction was different. It was also going to be a 2-span bridge, I believe. One span over the road and one span over some water. But that span I don't think was set yet. But it was similar in that the bridge over 9th Street was partially set, and the bridge over the road for FIU was also partially set. So it wasn't complete at the time of being reopened to traffic. So that's one way it was similar, but the differences are pretty stark.
Okay, so it looks like that's all we have for questions. Just a quick reminder, a link to the handouts and quiz can be found in your confirmation email, so just please complete the quiz by next Wednesday so I can email out your PDH certificates. I just want to say this was a great topic to kick off our virtual SE bootcamp, so thank you, Ryne, for a great presentation. Thank you to everyone who joined us today. For any SEs out there, we are having live webinars every Wednesday leading up to the renewal deadline. You can check out the available webinars on our website, and also keep an eye on your inbox. I'll be sending new announcements about webinars as they're added to our site. The next one will be on Wednesday, October 10th from 12 to 1 p.m. If you have any questions about our virtual bootcamp or you need help registering, please give us a call. Lastly, these webinars also satisfy PE requirements. So PEs, if you find a topic you're interested in, feel free to register as well. If you can't make it to the live version, we'll be offering webinars as on-demand products on our website, so you can just check back the following week. That's all I have, so thank you again, Ryne and everyone, and I hope you guys have a great weekend.
Thanks, Ariana.